Picture a hot, dense, ever-expanding soup of fundamental particles, a quark soup. That's what the universe was like, just a few million seconds after the Big Bang. But within this primordial broth, a remarkable transformation was underway. As the universe expanded, the soup cooled and quarks began combining to form protons and neutrons. Some of these new particles were flung together so violently that they created another kind of particle called an antiproton, which would normally annihilate with protons in a flash of light. But a rare few survived. And it turns out that protons and antiprotons are identical except for their electric charge. So a proton is a regular baryon, while an antiproton is a mouthful of antimatter. Since the universe we observe today is mostly made of matter, that means the very first stars and galaxies formed from the rare matter protons that somehow managed to survive the initial barrage of annihilations. The newly formed atomic nuclei captured electrons, and the first atoms were born. As the universe continued to expand and cool, those atoms eventually formed the first stars. But this early universe was a violent and dangerous place. There were lots of gamma rays floating around and other kinds of high-energy photons, which could knock electrons off of atoms and blast them through space. Eventually, the universe had cooled enough for those free electrons to combine with protons and form neutral hydrogen. And that turned the fog of the early universe into a clear window through which light could travel unimpeded. In other words, transparency was achieved, and we went from a universe of plasma to one filled with neutral gas. That transition took place when the universe was around 380,000 years old. And because light had been bouncing off of charged particles for so long before this, it couldn't travel far before being absorbed or scattered.
Ow.
But now the photons were free. They raced across the newly transparent universe and have been flying ever since. Today, they've stretched to microwave wavelengths and make up what we call the cosmic microwave background. The discovery of the CMB in 1964 by Penzias and Wilson earned them a Nobel Prize. They didn't know it at the time, but they had found the universe's baby picture. Astronomers today are still deciphering the secrets held within it. For example, because the CMB is so uniform, it tells us that the baby universe was extremely homogeneous and isotropic. In other words, it looked roughly the same in every direction and had no overall motion or preferred direction. This is surprising because today's universe does have these features. Galaxies spin and whirl, and they cluster together in ways that seem to violate the very homogeneity and isotropy of the CMB. How did order emerge from such a simple beginning? One leading idea is that the early universe expanded exponentially in a period known as inflation. During this brief instant, the universe would have been as small as an atom, and then expanded to its present size in a fraction of a second. This would have smoothed out any large-scale irregularities and set the stage for the more complicated structures we see today. But this raises another. What caused inflation? To answer that, some physicists have invoked a type of particle called an inflaton, which would have decayed after the rapid expansion ended, releasing the matter and energy that formed the first stars and galaxies. By measuring tiny temperature variations in the CMB, scientists may be able to put constraints on models of inflation and even settle which particles made up the original inflaton field. Other features of the CMB are helping astronomers map the distribution of matter in the universe today. In 1992, NASA's COBE satellite measured temperature variations across the entire sky. These maps showed that the early universe had some places that were slightly hotter and others that were slightly colder. These temperature differences were encoded in tiny variations in the density of matter. And by comparing those ancient variations to the distribution of galaxies today, astronomers can use the CMB to probe the nature of dark matter, the mysterious substance that makes up most of the matter in the universe. By studying the patterns imprinted on the CMB, scientists hope to solve one of cosmology's greatest mysteries. What is the nature of the universe's ultimate fate? Will the expansion of the universe continue to accelerate? Will it slow down due to the gravitational pull of matter? Or will it flip and cause the universe to collapse in on itself? Already, the European Space Agency's Planck satellite has provided evidence that the universe will expand forever. But the exact details of this cosmic destiny could become clearer as scientists continue to measure the tiny features imprinted on the CMB. For millennia, Humans have gazed up at the stars and dreamed of understanding the laws that govern the cosmos. Today, we're beginning to read the universe's oldest light, a baby picture left over from the dawn of creation. It's a humbling experience to realize that we can study the light that once illuminated the universe's tiniest moments. As we continue to analyze this relic radiation, we'll undoubtedly uncover more secrets about the birth of our universe. And who knows what other wonders the cosmos might reveal as we continue to explore it. We have digitized thousands of hours of educational programming from our archives and are making it available to you for free. A baby picture of the cosmos, tucked away in the archives of NASA. Goddard Space Flight Center is a canister filled with gold-plated mylar, a relic from a time when the fate of cosmology hung in the balance. Inside the canister is a single photograph of a faint glow that revolutionized our understanding of the universe. It was the first image of the cosmic microwave background. This photograph was taken in 1964 by Penzias and Wilson using a 70-foot antenna designed to intercept satellite signals. But instead of satellites, they picked up a hum from the cosmos. At first, they thought it might be interference from a nearby pigeon roost. After all, who would have guessed that a simple antenna could spy on the whispers of the Big Bang? This serendipitous discovery earned Penzias and Wilson the 1978 Nobel Prize in Physics. The cosmic radio waves they detected, later dubbed the cosmic microwave background or CMB, stretch back to just moments after the universe began. It's a baby picture of the cosmos. But for the next 3 decades, this baby picture was fuzzy, out of focus, difficult to interpret. All that changed in 1992 when NASA launched the Cosmic Background Explorer, or COBE. The COBE mission carried a single instrument designed to measure the entire sky. Over 15 months, it collected data that allowed scientists to produce the first detailed map of the white-tailed. Map of the white-tailed. COBE confirmed that the universe is truly only 1.4 inches, 3.5 centimeters in length, which corresponds to the size of a basketball. The map also revealed the existence of tiny hot and cold spots, supporting the idea that matter was distributed evenly throughout the early universe. These variations, known as anisotropies, are encoded with information about the early universe. They provide a wealth of knowledge about the formation of cosmic structure and the origin of the universe itself. With this remarkable legacy, COBE paved the way for future generations of CMB experiments to delve deeper into the secrets of the cosmos. One such experiment is the Wilkinson Microwave Anisotropy Probe, or WMAP. Launched in 2001, operating in an orbit around the L2 Lagrange point, WMAP provided an even more precise look at the CMB. Its mission lasted longer than expected. Operating until 2010, WMAP provided compelling evidence for the shape of the universe, confirming that it is flat. This finding aligns with the theoretical prediction of a flat universe based on string theory and the inflationary model. WMAP also helped refine measurements of the age and size of the universe, confirming values close to 13.7 billion years and 94 billion light-years respectively. Additionally, WMAP identified the first evidence for dark energy. By studying the cosmic microwave background, it detected a slight mismatch between the predicted and observed pattern. This discrepancy pointed to the existence of a force accelerating the expansion of the universe, now known as dark energy. WMAP's findings provided strong support for the lambda CDM model, the prevailing cosmological model today. However, it left some questions unanswered, including the nature of dark energy and the abundance of matter in the universe. Enter the Planck spacecraft, named after the renowned physicist Max Planck. This remarkable European Space Agency mission was launched in 2009, operating in a highly elliptical orbit. Planck ventured as far as Pluto and then returned to Earth's vicinity to observe the cosmos from a vantage point beyond the Moon's orbit. Planck embarked on its mission in 2009, and its primary science phase lasted for 8.5 months, during which it charted the polarization patterns of the cosmic microwave background. Once again, Planck delved deep into our universe's origins, providing invaluable insights into its evolution. The mission concluded its operations in 2013, but not before leaving behind an enduring legacy. On September 10, 2013, Planck revealed its final maps of the cosmos, marking a pivotal moment in space exploration. These maps showcased an extraordinary level of detail with the smallest angular scale ever measured and unprecedented clarity. Planck's groundbreaking work culminated in the release of its full scientific data set in 2015, laying the foundation for future studies. Planck's legacy continues to inspire astronomers worldwide, pushing the boundaries of human knowledge and our comprehension of the vast universe we inhabit. All three of these missions offer a treasure trove of information about the universe. The COBE mission gave us the first glimpse. WMAP painted a clearer picture, and Planck provided an incredibly detailed view. Together, they form a narrative of the universe's evolution from its fiery birth to the formation of cosmic structures. What do these maps tell us? What secrets about the universe are encoded in the CMB? How can we peer so far back in time? First, let's talk about the maps themselves. Each map represents a slice of the sky, a snapshot of the universe as it was when the CMB was born. Colors or shades of gray indicate temperature variations. Hotter regions appear red, and cooler ones blue. What might seem like a simple image is actually a wealth of information. The tiniest variations in temperature encode the seeds of galaxy formation. The universe was not completely homogeneous in the earliest moments. Tiny fluctuations in density, perhaps driven by quantum effects, caused variations in the light reaching us today. These minute differences were amplified by gravity over billions of years, eventually forming the galaxies and clusters we see around us. To quantify these temperature variations, astronomers use a parameter called delta T over T, which measures the difference in temperature between different parts of the sky relative to the average temperature of the CMB. By studying the pattern and distribution of temperature variations in the CMB, scientists can also estimate key cosmological parameters, such as the age, shape, and composition of the universe. For instance, the amount of matter and energy in the universe influences how the temperature variations are stretched and distorted. By analyzing these distortions, scientists can infer the relative abundance of matter, dark matter, and dark energy, which makes up the majority of the universe. The CMB also carries imprints of other cosmic events. For example, the scattering of CMB photons by dust in the early universe leaves a distinctive signature known as the dust budget. By measuring this signal, astronomers can estimate the amount of dust present in the early universe, which is crucial for understanding star and planet formation. Moreover, the CMB contains information about the abundance of light elements, such as hydrogen, helium, and lithium. These elements were produced in the first few minutes after the Big Bang during a process known as Big Bang nucleosynthesis. By analyzing the CMB's spectral lines, scientists can study the conditions and duration of this period, providing insights into the universe's early chemical evolution. Another fascinating aspect of the CMB is its polarization. Polarization happens when light waves oscillate along a particular direction. In the case of the CMB, the direction of oscillation can reveal information about the physical processes that affected the photons during their journey through the universe. For example, gravitational lensing by massive objects can distort and stretch the CMB, creating unique polarization patterns. By studying these patterns, scientists can map the distribution of dark matter and test models of gravity. Gravitational waves, ripples in the fabric of space-time, can also leave imprints on the CMB. These imprints occur as a minute stretching and squeezing of space that affects the polarization and temperature of the CMB. Detecting and analyzing these signals could provide direct evidence for the existence of gravitational waves and shed light on extreme cosmic phenomena like the Big Bang and the evolution of black holes. The search for gravitational wave signals in the CMB is an active area of research. The future of CMB research lies in new and upcoming experiments. These endeavors aim to measure subtle features in the CMB, to further probe the mysteries of the cosmos. One notable project is the Simons Observatory currently under construction in Chile. This cutting-edge facility will feature state-of-the-art telescopes and instruments designed to measure various aspects of the CMB with unprecedented precision. Another exciting development is the Square Kilometre Array (SKA), a massive radio telescope currently being built in South Africa and Australia. The SKA will have a total collecting area of about 1.19 square kilometers, making it the world's largest radio telescope. Its immense size and sensitivity will allow it to study the polarization of the CMB in greater detail, potentially shedding light on the inflationary epoch and the nature of dark energy. These advancements in CMB research demonstrate the tireless pursuit of knowledge and the relentless curiosity that drives humanity to explore the unknown. As scientists continue to analyze the data from these missions and embark on new endeavors, the hope is to unravel more of the universe's deepest secrets and gain a deeper understanding of our place in the grand scheme of existence. Okay, maybe not everything, but certainly the most distant thing we can see. It's the cosmic microwave background, or CMB, the faint glow that bathes the entire universe. Imagine this. You're standing in a dark room, staring out the window at a clear night sky filled with stars. It looks peaceful, but each star is actually a fiery ball of burning plasma 93 million miles away. And if you could see the light from that explosion that started those stars in the first place, it would look a lot like the CMB. In other words, it's the afterglow of the Big Bang. The CMB is everywhere, stretching in all directions and covering the entire sky. All that's left from the searing heat of the early universe. It's a relic of creation. But while we think of it as a picture, the CMB isn't really any kind of image we can see. With the naked eye, the CMB is faint microwave radiation with tiny variations in temperature. The average temperature is about 2.7 Kelvin, which is about 2.7 degrees Celsius, or 4.9 degrees Fahrenheit. Hotter than you'd expect a deep freeze to be, but definitely still cold. Each one transformed the way we see the cosmos, turning a mysterious background radiation into a cosmic blueprint. And there's more to come. So let's start with the first camera in our cosmic series. COBE, the blurry vision that changed everything. The story begins not with satellites, but with a mistake. Persistent noise in their microwave antenna. No matter where they pointed it across the sky, day or night, the noise was the same. At first, they thought it might be interference, even pigeon droppings inside the antenna. But cleaning it didn't help. What they had stumbled upon was the cosmic microwave background predicted years earlier by cosmologists like George Gamow and his collaborators. But the signal was crude, like hearing static on an old radio. To turn static into a picture, more precise instruments were needed. Enter COBE, short for Cosmic Background Explorer, NASA's first mission dedicated to mapping the CMB in detail. Launched in 1989, COBE orbited a point between the Sun and Earth called the Lagrange point. This kept COBE in a stable position relative to the Sun and Earth, allowing it to maintain a lock on the CMB without interference. First, measure the CMB spectrum, its exact distribution of wavelengths or colors. Second, detect tiny fluctuations in that background radiation. COBE's first measurement confirmed that the CMB is an almost perfect blackbody radiation curve. This was exactly what the Big Bang Theory predicted. It showed that the early universe was once in thermal equilibrium, like the glow of an ideal furnace. For millions of years, the universe was a sea of particles so dense and hot that nothing could escape. Light was absorbed and re-emitted over and over again. That burst of radiation was the CMB. The fact that it was still there, unchanged for billions of years, meant that nothing in the universe could travel faster than light. The speed of light became the ultimate cosmic speed limit. COBE also confirmed that the CMB came from all directions, meaning that no matter where you are in the universe, you will see the same view of the distant past. Finally, COBE detected what astronomers had been looking for all along: tiny ripples in the CMB's near-perfect temperature. The next step, sharper focus, enter the Wilkinson Microwave Anisotropy Probe, or WMAP. It launched in 2001 with the mission to measure the variations in the CMB with higher precision. As it cruised through space, WMAPs for instruments scanned the entire sky, mapping the celestial sphere in great detail. WMAP measured the entire sky about 200 times during its 9-year mission, constantly refining its image of the CMB. WMAP's resolution was about 22 arc minutes, about half as wide as a full moon in the sky. With this, it could clearly identify the acoustic peaks and troughs in the CMB's temperature pattern. These waves of hot and cold represented oscillations in the early plasma of the universe, a kind of cosmic heartbeat. They were created when photons and free electrons repeatedly bounced off each other, before the universe became transparent at 380,000 years. During that time, the plasma behaved like a fluid, and those waves, like sound waves rippling through a pond, left their mark on the fabric of space-time. The The scale and distribution of these ripples provided an abundance of new information. For example, the distance between peaks told scientists that the universe was accelerating rather than decelerating. Long before supernova provided visual evidence, by measuring the CMB's polarization, WMAP also shed light on the inflationary epoch, the period of exponential expansion in the universe's first fractions of a second. And in the case of the CMB, that direction could tell us which areas of the sky were being illuminated by light that was scattered off dust. Clouds in our galaxy, which would obscure our view of the CMB, WMAP found that dust only played a small role, confirming that the universe was largely transparent at the time the CMB formed. And finally, by comparing WMAP's map with the positions of galactic clusters, scientists could confirm the presence of dark matter. Dark matter, invisible and barely understood, makes up 27% of the universe's mass, but its presence affects how galaxies rotate and how light bends around massive objects. The CMB confirmed its existence, linking it to the distribution of matter throughout the universe. With WMAP's mission complete, it was time for the final masterpiece. Planck, the high-definition universe. While WMAP was orbiting Europe, was preparing its own satellite, Planck. Launched in 2009, Planck carried a single instrument optimized to see everything. A strategic move that minimized the effects of dust and allowed it to take measurements twice a year as the Earth moved around the Sun. This position gave Planck a unique advantage. It enabled the satellite to observe the CMB with unprecedented sensitivity and map the polarization pattern in greater detail. Planck observed the CMB in 14 frequency bands ranging from 30 GHz to 850 GHz, far beyond the range of radio telescopes on the ground. After collecting data for almost 3 years, Planck revealed its findings, a treasure trove of information about the universe. Its resolution was about 5 arc minutes, enough to see detailed patterns across the sky. The most striking was its confirmation of the previously identified peaks and troughs, now more accurately measured and better understood. Planck also confirmed the universe's geometry, showing that space is very close to flat. The universe is indeed a vast expanse with no obvious boundaries or edges, expanding uniformly in all directions. Furthermore, Planck helped refine the values of key cosmological parameters. Scientists were now able to determine the age of the universe with greater accuracy, putting it at about 13.77 billion years old. Planck also helped identify the chemical elements present in the early universe, primarily hydrogen and helium, as well as a small amount of lithium. These elements were forged in the furnaces of the first stars and were released into the universe, when those stars exploded as supernova, enriching the cosmic landscape with the building blocks of life. So what does the future hold for CMB research? Now that we have such high-resolution pictures of the CMB, we can look for details that may reveal new insights into the nature of the universe. One intriguing possibility is the search for anomalies in the CMB's temperature distribution. Some scientists have suggested that certain regions of the sky show unusually low temperatures, hinting at the presence of large voids or exotic phenomena in the early universe. Others are studying the CMB's polarization to learn more about inflation and the universe's accelerated expansion. By analyzing the pattern of polarization, researchers hope to uncover the nature of dark energy, the mysterious force driving the accelerated expansion. Additionally, missions like the Simons Observatory and the Square Kilometre Array will conduct near and far-side CMB experiments to, precisely, measure the polarization of the CMB. They will be looking for B modes, a type of polarization that could provide evidence of gravitational waves generated during inflation. The search for these elusive signals is like looking for a needle in a haystack, but the stakes are high. Discovering evidence of inflation would not only confirm some aspects of the Big Bang theory, but also open up new avenues in cosmology. It could also potentially lead to a deeper understanding of the fundamental laws of physics. We tend to think of the universe as vast and empty, but make no mistake, it's incredibly crowded. From galaxies to gas clouds and everything in between, there's a lot out there. And to understand how all this stuff came to be, scientists turn to the cosmic microwave background, or CMB. This leftover glow from the Big Bang gives us a glimpse into the universe's baby pictures and holds secrets to the very creation of the cosmos. The CMB is what's left of the light that was released just 400,000 years after the Big Bang. Before that, the universe was a hot, dense soup of particles. Light couldn't travel freely through this primordial haze, so it didn't exist in the way we know it. Once the universe cooled enough for protons and neutrons to form, things changed dramatically. These simple nuclei acted as seeds around which electrons could gather. And when they did, the light that was bouncing around got a chance to escape. This sudden burst of radiation decoupled from matter, creating a bright fireball that bathed the universe in its glow. As the universe expanded, this light stretched and cooled over time until today, when it reaches us as faint microwaves. We can see this ancient light everywhere. It comes from every direction and fills the entire sky. But that doesn't mean the CMB is uniform. If you look closely, you can see tiny temperature variations, as little as 1 part in 100,000. These ripples encode information about the distribution of matter in the early universe. Over billions of years, gravity has amplified these tiny variations, pulling together clumps of matter that eventually formed the galaxies, stars, and planets we see today. In fact, the CMB is the most detailed map we have of the early universe. It reveals a breathtaking vista of nearly perfect smoothness, which raises 2 crucial questions. How did this smoothness come about, and why is it so incredibly smooth in the first place? To answer the first question, we need to travel back to the tiniest fractions of a second after the Big Bang, a time known as inflation. Imagine the universe expanding faster than the speed of light. That's how quickly it grew during inflation. Space itself stretched, creating huge ripples of quantum fluctuations. These ripples stretched across the sky, and we can see their imprint today as the tiny temperature variations in the CMB. Once inflation ended, these quantum fluctuations became the seeds of cosmic structure, eventually growing into the galaxies and clusters of galaxies we observe today. So the CMB tells us that the early universe wasn't smooth. It was a frothy mix of quantum fluctuations. But here's where things get really interesting. These quantum fluctuations should have been smoothed out after just a few minutes due to a process called diffusion. Think of it like pouring a cup of hot cocoa into a cold mug. The cocoa represents the heat, or in our case, the variations in the early universe. The mug represents the rest of the universe. Initially, the cocoa is only on one side, but over time it diffuses throughout the entire mug. It becomes more evenly distributed. In the same way, the variations in the early universe should have spread out and vanished, leaving behind a smooth and featureless CMB. But that's not what we see. Instead, we find tiny temperature variations frozen in time. How can this be? Scientists think the answer might lie in a process called preheating. During inflation, some particles were accelerated to unimaginably high energies. They then decayed into normal matter, heating up the universe. If this happened very quickly, the heat would not have had time to spread out, leaving an imprint on the CMB that we might be able to detect. Finding this preheating signal would be monumental. It would confirm key aspects of inflation, showing that the quantum fluctuations responsible for the structure of the universe arose from particle interactions during this brief period of exponential expansion. So there you have it. The CMB, a window into the baby pictures of the cosmos, revealing the secrets of the early universe. With each new observation, scientists piece together a more complete and accurate picture of how the universe began. But as they do, they uncover new mysteries and unexpected features, reminding us that the quest to understand the origins of the universe is a never-ending journey. This is the cosmic microwave background, our universe's oldest light. At first glance, it's featureless, just a faint glow that bathes the cosmos in every direction. But look closer. Those faint variations encode a wealth of information, an ancient story written in photons more than 13 billion years old. And this story has Earth written all over it. The conditions that prevailed when the universe was just a few 100,000 years old, conditions imprinted on the cosmic microwave background, or CMB, set the stage for everything that followed for stars and galaxies, for chemistry and complex life, and for our place in the grand scheme of the cosmos. Structure from tiny fluctuations, the most obvious features on the map are those tiny temperature variations. They may seem like mere ripples in the fabric of space, but they are far from insignificant. They are the seeds from which the entire structure of the universe grew. To understand why, let's go back to the beginning. In the first few minutes after the Big Bang, the universe was a hot, dense soup of fundamental particles. But soon the universe started to expand, cooling the plasma and allowing particles to combine into atoms. This process is called recombination. And as the universe continued expanding, the light released during recombination began to stretch, shifting from higher energies to lower energies and moving into the microwave part of the spectrum. This ancient light, now some 13 billion years old, is what we know today as the cosmic microwave background. But those tiny temperature variations seen across the CMB were not present during the Big Bang. They arose during the universe's inflationary period, a brief but explosive episode of expansion that occurred just a fraction of a second before the onset of recombination. The exact mechanism driving inflation is unknown, but the result is observable in the CMB. Tiny quantum fluctuations in the energy field driving inflation, stretched and amplified during the subsequent expansion, creating small overdensities in the fabric of space-time. These density variations, though minuscule, were significant. They provided the gravitational seeds needed to pull together the universe's matter into the first stars, galaxies, and planetary systems. Regions with slightly higher densities attracted matter through gravity, gradually growing into vast cosmic structures. Over millions of years, these massive overdense regions evolved into the web-like filaments and halos of dark matter that still pervade the universe. Within these filaments, ordinary baryonic gas cooled and condensed, collapsing into the first luminous objects, stars and galaxies. Without these primordial density fluctuations, the universe could have been sterile, devoid of large-scale structure, and perhaps even devoid of life. If the variations had been smaller, gravity would not have been strong enough to overcome the outward pressure of matter, preventing the formation of galaxies. If the variations had been larger, matter might have collapsed too rapidly into supermassive black holes, leaving little room for the formation of anything else. In essence, the structure of the CMB provided the universe with its architecture, setting the stage for everything that followed. It's an ironic twist that the universe's homogeneity is maintained despite the existence of these fluctuations. The reason lies in the nature of the fluctuations themselves. They are random, spread evenly across the sky. This randomness ensures that any given location is just as likely to be inside a galactic filament as it is to be in an intergalactic void. In other words, while the universe may be inhomogeneous on the largest scales, there are no preferred locations for structure. This lack of preferred locations ensures that, statistically, regions will evolve in a similar manner. Over time, this leads to a universe that, on average, is hospitable and homogeneous, enabling the emergence of complex structures like Earth within its vast expanse. The recipe of elements, the cosmic microwave background, does more than just dictate the structure of the universe. It also reveals the abundance of elements forged in the fiery crucible of the early cosmos. As we discussed earlier, by the time of recombination, the universe had already produced significant quantities of hydrogen and helium. These two elements, along with traces of lithium, were the building blocks of the cosmos. But the recipe didn't stop there. The faint glow of the CMB witnessed the birth of the first stars, which would go on to enrich the universe with heavier elements. When stars like our Sun fuse hydrogen into helium, they produce a small amount of heavier elements, primarily carbon, nitrogen, and oxygen. These elements are vital for life as we know it. After a star like our Sun exhausts its hydrogen fuel and collapses, the core continues to produce elements up to iron through a process known as the triple alpha process. Heavier elements beyond iron are created in the explosive deaths of more massive stars. These supernova hurl elements into the interstellar medium, seeding the cosmos with the ingredients for future generations of stars and planetary systems. The abundance of these elements imprinted in the CMB provides a snapshot of the early universe's chemistry. By analyzing these abundances, astronomers can trace the evolution of the universe from its simplest forms to the emergence of complex elements. The CMB thus serves as a reminder that the universe's story is one of continuous evolution and enrichment. Our solar system's ancestry. As the universe evolved, the Milky Way formed, a sprawling disk of stars bound together by gravity. Like the rest of the cosmos, the Milky Way's structure is a reflection of the conditions established in the CMB. The density distribution of the early universe led to the formation of a galactic scaffolding, a framework of massive clusters and filaments that acted as the foundation for the Milky Way's assembly. Within this scaffolding, successive generations of stars enriched the galaxy with metals, a term astronomers use to refer to elements heavier than helium. About 4.6 billion years ago, a molecular cloud in the Milky Way's spiral arm collapsed, giving birth to our Sun and the planets. This collapse was a direct consequence of the density ripples in the CMB, which ensured that the Milky Way's structure was not uniform, but rather had the clumpiness necessary for star and planet formation. In other words, our very existence is rooted in the CMB's faint whispers, which echoed the conditions that prevailed just moments after the Big Bang. If the CMB had been featureless, the Milky Way might never have formed. Or if it had shown a different structure, Earth's place within the galaxy could have been vastly different. Instead, we find ourselves in a solar system cradled by the echoes of the universe's birth. Our ancestry written in the language of the cosmos, radiation, and the conditions for life. The conditions encoded in the CMB also played a crucial role in determining how hospitable the universe could be for life. The balance between dark matter and radiation in the early universe influenced the timeline of galaxy formation. Galaxies serve as the primary sites for star formation and planet formation, making them essential for life's emergence. On the other hand, excessive radiation could have prevented the formation of stable planetary systems, disrupting the delicate conditions necessary for life to flourish. Moreover, the uniformity of the CMB points to a cosmological principle, a statistical sameness across vast regions of space. This principle ensures that no region of the universe was too chaotic or too isolated to preclude the possibility of life. It guarantees that over billions of years, the universe could settle into a state conducive to the development of complex structures like Earth. If the CMB had revealed a highly inhomogeneous or rapidly evolving universe, the long-term stability of Earth-like planets could have been compromised. Instead, we exist in a universe shaped by the delicate balance of forces imprinted on the CMB, a universe where the conditions for life are not only possible, but statistically probable. The CMB and Earth, a deepest connection. Ultimately, the story of the CMB and Earth is a story of deep connection. Everything on Earth, every atom in our bodies, every molecule in our atmosphere, all began as hydrogen created in the fiery furnace of the Big Bang. The faint glow of the CMB witnessed the birth of stars and galaxies, the engines that forged the heavier elements essential for life. Even our place in the Milky Way is tied to the primordial imprints left on the CMB. In studying the CMB, we are not looking at something distant or foreign. We are looking at the direct ancestor of our world, the universe as it was, when Earth was just a glimmer in the cosmic tapestry. When we decipher the secrets of the CMB, we are uncovering the very essence of our cosmic origins. We are discovering the conditions that made planets, oceans, and people possible. The CMB is quite literally our cosmic DNA, a record of the universe's earliest moments and the foundation on which our existence is built. The more we learn about the CMB, the deeper our understanding of Earth's place in the cosmos becomes. We realize that our story is not just about Earth or even the solar system. It's about the universe as a whole. We are part of a grand cosmic narrative that began with the Big Bang and continues to unfold before our very eyes. The faint glow of the cosmic microwave background may seem like a distant, abstract phenomenon, but it is anything but. It is a direct connection to our cosmic ancestry, a reminder that we are part of something much larger than ourselves. The story of the CMB and Earth is a story of profound interconnectedness, where the conditions of a newborn universe echo through time to shape the world we call home. And as we continue to explore the mysteries of the cosmos, we can be sure that this story will continue to deepen, revealing new insights into our place in the grand scheme of things. For billions of years, the cosmic microwave background bathed our planet, a silent, invisible visitor from the dawn of time. Yet we lived oblivious, lost in the cradle of our own making, too young to see, or too clever to imagine what might be beyond. So how did we discover it? How do we map its secrets? What can these maps tell us about ourselves? Let's find out. The human gaze discovery of the CMB, the cosmic microwave background, existed for nearly 13.8 billion years before anyone knew it was there. Every night, it washed invisibly over Earth. For most of human history, no eye, no instrument, and no imagination even suspected its presence. The journey from ignorance to discovery, and finally to precision mapping, is one of the greatest scientific sagas of the 20th and 21st centuries. The first clues. Theory before observation, the possibility of a leftover cosmic glow, was first suggested in the 1940s. Physicists George Gamow, Ralph Alpher, and Robert Herman predicted that if the universe began in a hot, dense state, then the radiation from that fiery birth should still be detectable today. They even estimated its temperature around 5 Kelvin. But in the 1940s, few people were interested in cosmology, and their papers attracted little attention. For nearly 2 decades, the idea lay dormant, buried in academic obscurity. The accidental discovery, Penzias and Wilson in 1964, 2 engineers at Bell Labs in New Jersey. Arno Penzias and Robert Wilson were working on a sensitive microwave antenna. They were not looking for echoes of the Big Bang. They were simply trying to eliminate noise in their radio receiver. No matter where they pointed the antenna toward the galactic plane, away from it, at the sun, at the night sky, the noise remained. It was faint, isotropic, and constant. At first, they suspected earthly interference. Then they wondered if pigeons nesting in the antenna were responsible. They removed the pigeons. The noise persisted. What they had stumbled upon was the fossil radiation of the universe itself. Meanwhile, just 40 miles away at Princeton University, physicist Robert Dicke and his team were preparing to build an instrument specifically to search for this predicted radiation. When they heard about Penzias and Wilson's unexplained signal, they immediately realized what it was. Dicke reportedly turned to his colleagues and said, "Well, boys, we've been scooped." In 1978, Penzias and Wilson were awarded the Nobel Prize in Physics for their discovery. COBE, the first baby picture of the universe, the discovery of the CMB, was only the beginning. The next step was to measure it with precision. In 1989, NASA launched the Cosmic Background Explorer, COBE satellite. COBE carried instruments capable of mapping the spectrum of the CMB and measuring its anisotropies, the tiny temperature fluctuations across the sky. 2 results from COBE changed cosmology forever. Perfect blackbody spectrum. COBE confirmed that the CMB follows a blackbody curve at 2.725 Kelvin with exquisite precision. This was proof that the radiation truly came from a hot, dense origin. First detection of anisotropies, COBE revealed the faint ripples in the CMB, the tiny variations in temperature that correspond to the seeds of galaxies. These achievements earned John Mather and George Smoot the 2006 Nobel Prize in Physics. Smoot famously remarked, "If you're religious, it's like looking at God." WMAP high-resolution mapping launched in 2001. The Wilkinson Microwave Anisotropy Probe, WMAP, provided a far sharper view. Over 9 years, WMAP mapped the sky in multiple frequency bands, removing galactic foregrounds to isolate the CMB signal. WMAP's results pinned down key cosmological parameters with extraordinary accuracy. The age of the universe, 13.8 billion years. The composition of the universe, approximately 5% ordinary matter, approximately 27% dark matter, approximately 68% dark energy. The geometry of the universe, flat, within a small margin of error. WMAP gave cosmology its standard model, a framework as powerful as the standard model of particle physics. Planck, the gold standard of precision, in 2009. The European Space Agency launched Planck, the most sensitive CMB satellite to date. Planck mapped the entire sky with unprecedented resolution, detecting fluctuations as small as a few millionths of a degree. Its final results, released in 2018, refined our understanding of cosmological parameters, confirmed the universe's age, and revealed subtle anomalies like the CMB cold spot that remain subjects of debate. Planck's maps are the most detailed baby pictures of the universe we have ever taken. Beyond satellites, new frontiers of observation, ground-based observatories, and balloon-borne experiments continue the work. Instruments like the South Pole Telescope, Atacama Cosmology Telescope, and BICEP series focus on polarization, the swirling patterns in the CMB that may contain signatures of gravitational waves from inflation. This next frontier could connect the physics of the very early universe to Einstein's theory of gravity and even to quantum mechanics. Mapping the cosmos, one of the remarkable things about the CMB is that we have been able to map its temperature. Variations to such high precision that we can use these maps to study the distribution of matter in the universe. By studying the variation in temperature, we can see how the first stars and galaxies formed. Of course, we cannot see inside of these structures, but we can see what lies above and below them. With enough observations, we can construct a three-dimensional map of the universe. Anisotropies and seeds of galaxies, the cosmic microwave background is almost perfectly homogeneous, meaning that it looks roughly the same in every direction. However, there are tiny variations in temperature, a few tenths of a millikelvin across the sky. These anisotropies in the CMB are extremely important because they contain the imprints of the first large-scale structures that formed in the universe. These are the seeds of the galaxies and galaxy clusters that we see today. They are the roots of the web-like structure that stretches throughout the cosmos. The pattern of these anisotropies is remarkably complex, and scientists are still working to understand all of its features. Some of the patterns are smooth and some are more lumpy. Some are hotter and some are colder than the average temperature of the CMB. All of these features provide clues about the physical processes that occurred in the early universe. For example, the smooth features are thought to have arisen from the movement of matter in the early universe, while the lumpier features are thought to have come from the clumping of matter into the first stars and galaxies. By studying these anisotropies, scientists hope to learn more about the fundamental properties of the universe, such as its age, its size, and its composition. They also hope to learn more about the physics of the early universe and the processes that led to the formation of the first galaxies. What can we learn from the CMB? The cosmic microwave background is a treasure trove of information about the early universe. By studying its temperature, anisotropies, we can learn a great deal about the composition and evolution of the universe. Here are just a few of the things that scientists have learned from the CMB. The universe is flat. One of the most important pieces of information that we have learned from the CMB is that the universe is flat. This means that the universe has a very particular geometry. If the universe were curved in any way, it would have looked different from what we actually observed. The fact that the CMB is so uniform tells us that the universe must be flat. The universe is homogeneous. Another piece of information that we have learned from the CMB is that the universe is homogeneous. This means that it looks the same in all directions and at all points. If the universe were not homogeneous, we would have seen this in the CMB. The fact that the CMB is so homogeneous tells us that the universe must be the same everywhere. The universe is made up of more than just matter. One of the most surprising discoveries that we have made about the universe is that it is not made up of just matter. In fact, we now know that the vast majority of the universe is made up of dark energy and dark matter. We can see the effects of dark energy and dark matter in the way that the universe is expanding. We can also see its effects in the CMB. The fact that we have been able to detect dark energy and dark matter in the CMB is one of the most remarkable achievements of modern cosmology. The universe is older than we thought. Finally, we have also learned that the universe is much older than we once thought. We now know that the universe is about 13.8 billion years old, and we have been able to determine this age by studying the CMB. The fact that the universe is so old tells us that there is a lot more to explore out there. There are many more galaxies, stars, and planets than we can even imagine. The future of CMB research, the research of the CMB, is an active area of research, and there are many exciting things that scientists are working on right now. One of the most exciting areas of research is the study of CMB polarization. Polarization is a property of light that tells you how the light waves are vibrating as they travel. When light passes through a medium, such as gas or dust, the waves can be twisted, and this will affect the polarization of the light. By studying the polarization of the CMB, we can learn about the conditions in the early universe and the processes that occurred at that time. Scientists are also working on more precise measurements of the CMB. The more precise we can make these measurements, the more we will be able to learn about the early universe. For example, one of the things that scientists are looking for is a signal from the inflationary epoch. Inflation is a period of rapid expansion that is thought to have occurred in the first few seconds after the Big Bang. If we can detect a signal from inflation in the CMB, it will provide strong evidence for this theory. The legacy of the CMB, the discovery and mapping of the CMB, is one of the greatest achievements of modern science. It has taught us so much about the early universe and has revolutionized our understanding of cosmology. As we continue to study the CMB, we can be sure that we will make even more exciting discoveries in the years to come. So keep your eyes on the skies and your mind open to the possibilities. Who knows what wonders we will find next? In 1964, Arno Penzias and Robert Wilson discovered a faint hiss of radiation permeating the cosmos. A whisper from the dawn of time known as the cosmic microwave background, or CMB. At the time, they had no idea just how big a deal they'd actually found. It was just background noise, literally. They were trying to build a satellite communications system, and that constant hiss was interfering with the signals. Little did they know that sound would become humanity's most important clue to understanding the birth of the universe. The CMB is basically a baby picture of the cosmos. It's one taken just 400,000 years after the Big Bang. Today, scientists use highly sophisticated equipment to detect and study this ancient light. So far, it's provided many insights, such as the age and shape of the universe. But it's not done speaking. The CMB is like an ancient text, most of it translated, yet key passages remain hidden. The next generation of experiments aims to read those missing lines, and in those lines may lie answers to the deepest mysteries of physics. One of the biggest open questions in science today is whether the universe was created by a process called inflation. To make a long story short, inflation posits that the universe expanded exponentially in its first fraction of a second, smoothing out any initial wrinkles and setting the stage for everything we see today, but we have no direct evidence for it. That is until now. You see, the physics of inflation predicts that the rapid expansion would have generated ripples in space-time known as gravitational waves. These waves would have left an imprint on the CMB, and we on the verge of finding it. How do we know this imprint will be a swirl pattern called B-mode polarization? Imagine squeezing a balloon. The lines on the balloon represent space-time. Okay, as you squeeze it, those lines stretch and distort, creating a swirling pattern. That's kind of like B-mode polarization. By contrast, another type of polarization called E-mode looks like this. It's more orderly and curl-free. Now, while we haven't found the primordial B-modes predicted by inflation, we have detected E-modes. This happened back in 2014 when the BARC-2 experiment at the South Pole detected a signal in the CMB that looked an awful lot like B-modes. Fortunately, that signal turned out to be dust within our galaxy, leaving scientists empty-handed and embarrassed. The lesson was clear. Detecting these faint signals requires extreme precision, global collaboration, and careful separation of cosmic whispers from galactic foregrounds. Today, upgraded instruments like BARC-3, the Keck Array, and the Simons Observatory continue the hunt. However, even if they don't find anything, it won't mean that inflation didn't happen. That's because a European Space Agency mission called Planck also looked for these B-modes and failed to find them. Yet it still gave us some pretty strong evidence for inflation. You see, Planck measured something called the temperature anisotropy of the CMB, essentially how much the temperature varies across the sky. It found that the temperature variations were smaller than expected without inflation. So while we don't have a smoking gun, we have circumstantial evidence that adds up to a pretty strong case. If we want to find those primordial gravitational waves, though, we need to look beyond the CMB temperature. It's because there are other signals hidden within the light, specifically a type of wave called a tensor. Yes, there's another type of wave besides gravitational waves. No, they aren't some new age woo-woo. They're a real part of general relativity. But unlike gravitational waves, tensor modes don't affect the CMB temperature, they affect the polarization. This makes them super hard to detect, which is why we haven't found them yet. According to Einstein's theory, all types of waves should exist, but we've only ever confirmed gravitational ones. So detecting tensors would be an incredible achievement and revolutionize our understanding of the universe. Fortunately, we have a few promising experiments on the horizon. One is LIGHTBIRD, a space-based mission being planned by the Japan Aerospace Exploration Agency. JAXA, set for launch in the 2030s, LIGHTBIRD is designed to measure CMB polarization with unrivaled precision, focusing squarely on detecting those elusive B-modes. It will carry 3 instruments to map the polarization of the CMB, each sensitive to different frequencies. This will help distinguish between the various types of waves and separate the signal from noise. Another exciting project is CMBS-4, a ground-based observatory currently under development and set to begin operation in the 2020s. CMBS-4 won't be a single telescope, but rather a network of at least 3 experiments distributed across multiple telescopes in Chile and Antarctica. One of the telescopes, the Simons Observatory in Chile, is already in operation and is taking some amazing pictures of the cosmos. The observatory features a 600-foot dome housing, several telescopes that can observe nearly half of the sky at once. Together they can measure the temperature and polarization of the CMB with unprecedented accuracy. All of these upcoming experiments will work together to measure every aspect of the CMB, giving us a more complete picture of the early universe. But what if we take this a step further and send a probe to the moon? Would we get a clearer view of the CMB from there? Well, it turns out a small team of physicists have proposed just that. The mission, dubbed PICO, stands for polarimetry of the cosmic microwave background. It's a NASA concept that would send a small satellite about the size of a bread box to the moon's far side, and use a large deployable mirror to map the CMB across the entire sky. The main instrument on board would be a polarimeter capable of measuring both E and B mode polarization across dozens of frequency bands. But how would this help us understand the universe better? Well, it turns out the moon could offer a huge advantage over Earth-bound telescopes. You see, the moon doesn't have an atmosphere, which means there's no atmospheric interference with the satellite's measurements. Additionally, by positioning the satellite on the far side of the moon, it would be shielded from radio waves emitted by Earth, which could otherwise interfere with observations. Plus, it would eliminate the need for the satellite to perform a complicated and risky orbit that would otherwise be required to avoid Earth's atmosphere. As you can imagine, not having any atmosphere or radio wave interference would allow the satellite to get a much clearer view of the CMB. It would be able to map the entire sky with unprecedented detail and accuracy, which would help scientists better understand the physics of the early universe. Of course, before we start packing our bags for the moon, we need to consider the cost. While NASA hasn't put an exact price tag on the project, it's safe to say it wouldn't be cheap. Launching a satellite to the moon is no easy feat, and the cost would likely run into the hundreds of millions, if not billions of dollars. That's why PICO is still just a concept at this point. It would require a lot of funding and approval from NASA and other space agencies. Still, it's an intriguing idea that could potentially revolutionize our understanding of the universe. Whatever comes next, the future of CMB research is bright. With each new discovery, we come closer to understanding the origins of the universe and our place within it. Some people are calling the CMB a miracle. They say the universe fine-tuned itself before we arrived to ensure that life could evolve. After all, if the universe was even slightly different, stars wouldn't form, galaxies would fly apart, and life couldn't emerge. But others disagree. They argue that life arose by chance in a vast, uncaring universe. So which is it? Are we special or just lucky? It's hard to say. The CMB doesn't offer any clear answers. Its faint glow doesn't reveal the presence of intelligent design. But maybe that's not the point. Maybe the CMB teaches us something else entirely, namely, that we are children of the cosmos, born from the same stuff as stars and galaxies. We evolved from the same primordial soup that gave rise to everything else in the universe. We are not special, we are just here. And that realization should fill us with awe. So what do you think? Is there a deeper meaning to the CMB? So let me know in the comments below. And speaking of meaning, there's a website that wants to give you more of it. See, they believe that everyone should have access to accurate and reliable information. That's why they VA partnered with news organizations around the world to create a website where you can find the most important stories of the day in a clear and concise format. What's more, the website is ad-free and subscription-based, which means you won't be bombarded with ads or have to worry about fake news. Instead, you'll get a carefully curated selection of the most important stories from the previous day delivered straight to your inbox. And the best part? You can customize the topics and sources you want to see, ensuring that you never miss a beat. I hope you enjoyed this video. If you did, please remember to subscribe and hit the bell icon for more videos like this. Thank you for watching, and I'll see you next time.